people can join in. Well, welcome everybody to today's webinar on do you have a run to fail policy for your SIS? And the other bit should be, and if you do, why? We're just going to go through and look at the reasons behind why this is not good practice. Just a brief introduction. Myself, Steve Gandy, I've 40 years experience now in controls and safety. Background was in designing software and hardware for emergency shutdown, fire and gas, and safety systems in general. I am now with Exida, have been for the last 5 years. I'm also the VP of Business Development globally and look after our end user side of things. I'm one of the primary trainers for our FSC 100 course that we do, which leads to the certification. A little bit about Exida. We are global. We have offices around the world, and we've been in business for about 18 years. Primarily when we started Exida, it was to help manufacturers, but since then it's grown significantly, and we do certification for products not only on the functional safety side to IEC 61508, but also on the cybersecurity side to IEC 62443. We are accredited by ANSI, which is part of the International Forum of Accreditation, to do this work, because again, who certifies the certifier? We also have products that support the full safety life cycle with Excellencia and help with the operations and maintenance side through SILSTAT. We also have 3 main service divisions that look after functional safety, cybersecurity, and alarm management. And we've worked with a variety of different types of end users, OEMs, engineering contractors, etc., in a variety of industries. We do provide a lot of information which is free. I mean, these webinars that we do is one source, and these are recorded and held on our website under the resources section. We also provide consulting services, as I've mentioned, the engineering tools, the certification, and training. We provide training in all 3 disciplines of functional safety, alarm management, cybersecurity, and we've also published a number of books and have white papers available, as well as our SERH, which is our Safe Equipment Reliability Handbook that has all the failure rates for different types of devices that you would find in process applications. We've established a scheme for certification for functional safety and cybersecurity, and that extends now not only to the equipment, for example, but also to personnel, because we have the certified functional safety expert, certified functional safety professional, and now we've introduced the controls automation cybersecurity expert and controls automation cybersecurity specialist, which are equivalent to the CFSE and CFSP, but only on the cybersecurity side. In terms of reference materials, I've mentioned the books. We have a number of books that are available through the website, and of course the SCRH, which is also available. Engineering tools, we provide the full safety lifecycle tool, which is our Excellencia tool. Some of you may be familiar with it, but it covers the analysis phase, the design and implementation phase, and of course the operation and maintenance phase. So with that, let's get to the main subject. Do you have a run to fail policy? And if you do, really, why is that? Well, let's look at the objectives of the safety life cycle. We know that in the past we've had problems with systems where we've had issues regarding, for example, systematic problems. The systematic is the 3 Ps, where we look at the personnel, in other words, how well trained are they, how competent are they, the procedures, are there procedures that are being followed, and the paperwork, is there adequate documentation. So this would apply to, for example, design specifications. Do we have a design specification that has been reviewed correctly, that has been implemented correctly? Is our manufacturing good enough? Is our quality system good enough? Because the point is we're trying to build more cost-effective systems that match our design with our risk in an economic fashion. And also we want to try and safeguard against random faults by improving the product quality as far as possible. So these are the purposes of the safety life cycle. We're trying to get to a consistent methodology whereby we can design and implement a safety instrumented system with safety instrumented functions to achieve the amount of risk reduction and protection we're looking for. So that's the basic purpose. Now when it comes to how do we calculate and work out what protection we have in terms of our safety integrity levels for our SIFs, our safety instrumented functions, we use what's known as probabilistic calculations to predict these likelihoods of failures. And in the process industry, most of the time we're looking at what's known as low demand, whereby the demand on the SIF won't be any more frequent than once per year or at least twice the proof test interval. And then in these low demands we use the probability average. We use a probability of failure on demand average, a PFD average. And that PFD average uses failure rate data. And this is based upon the concept of a constant failure rate during useful life. And we're going to look at that in a minute as to what that means. And of course, constant failure rate is determined based upon either real data or predictive data. And there we now have over 200 billion unit operating hours of data available to draw on. So we can be pretty accurate. And the reason we look at this is because if you consider what's known as the bathtub curve. Now typically when we look at failures, and this is something that's been seen consistently, you'll see, and in this case we've taken an example of 30 units and we've recorded how many hours they operated before they failed, and as a result of that we were able to determine a failure rate over this period of time. And when it's plotted, what you can see is initially we have a relatively high portion of failures, and then it sort of flattens out a little bit, an odd anomaly here, and then at the back end it suddenly jumps up. So why is that? Well, the concept of the bathtub curve is that we talk about these front end failures as being infant mortality. These are the units that will fail fairly early on due to weaknesses in the components, and normally most manufacturers, before they ship any product, they will do some form of either temperature cycling, whereby they'll put it in an environmental chamber and they will cycle it up and down for 24 or 48 hours. The point being that these stresses will wheedle out the weaker units, and most manufacturers want to do that before these units get out into general population, because of course they don't want warranty returns. So the weaker units are wheedled out at the front end. But again, at some point the failures are going to go up again, and at this point this is what we call wear out. This is where the product strength has weakened to the point now where the environmental stresses or the normal stresses of operation are beginning to take their toll. And so we see a sharp rise at the back end. The bit in the middle here is what we use as our useful life. So useful life is when you have a steady, declining or constant failure rate over a period of time, and as you can see here it's relatively flat. So this is known as useful life, and manufacturers will publish their useful life in their safety manual. People who have been on my training courses are very familiar with my term of RTFM, which is read the flaming manual, because the safety manual has all the relevant data and information you need to be able to design your system. So from a probabilistic analysis point of view, we take a simple approximation, and what this does is it actually gives us a more pessimistic result. We know that we can wheedle out our infant mortality through front-end quality procedures such as burn-in, run-in, and even at site when you do the initial commissioning tests. Also, through the safety life cycle, we can find these weaker devices by creating proof tests, and we're going to talk about proof tests a little later on. So therefore, if you see here, if we take this average and then we approximate here, you'll see we're actually pretty pessimistic. And that's not a bad thing, because we need to be pessimistic or as realistic as possible. So we take a pessimistic approximation from a constant failure rate based upon this average. So you can see, if we take this approximation over this period of time before we start to rise up, this is our defined useful life. After which you need to replace or refurbish the unit. So the manufacturer, as a result of the IEC 61508 2010 standard change, manufacturers now have to include the useful life in their safety manual. So taking that then, when we talk about mean time to failure, we talk about the time the device should be operating for before it fails. And again, this is predicated on a constant failure rate assumed during our useful life, in which case we can directly relate our mean time to fail to being inversely proportional to our failure rate lambda. And if we were interested in dangerous failures, then it would be our mean time to fail dangerously, our MTTF-D, would be equal to 1 over our dangerous failure rates, which would be lambda D. So you can see here a pressure transmitter has a total of 5 times 10 to the minus 7 failures per hour, or what we would say is 500 fits. Basically we take a measurement of a failure over 10 to the 9 hours, or a billion hours, and so a failure rate per hour would be 10 to the minus 9 that we refer to as a fit. It's just an easier way of representing a failure in time. So we say, in this case, 500 fits. So obviously if we have 500 fits, what's the mean time to fail? And that would be the equivalent of 2 million hours if we take 1 over 500. And that's approximately 228 years if you divide it by 8,760, number of hours in a year. Now, of course, this is not saying that a pressure transmitter will last 228 years. It's just saying that the useful life is going to be different from that. So, for example, if you had 100 transmitters, then you'd expect to get a failure every 2.28 years. So this is a different metric compared to useful life. But here again, this is predicated on a constant failure rate during the useful life. So if we now look at, we have a safety instrumented system with safety instrumented functions. So what would the probability of an accident be? Well, obviously if a hazard occurs and the automatic protection function operates, then we don't have an accident because we've prevented it. But if an accident or a hazard occurs, rather, and the function fails, then we're likely to get an accident, because remember, of course, our safety instrumented functions are our last line of defense most of the time. So we need to know the probability of failure of that function. So we could say that the probability of our hazard multiplied by the probability of failure on demand of our SIF would be the probability of the accident. The question then becomes, what is the probability of failure on demand of our safety instrumented function? And here again, when we're doing the probabilistic analysis or the SIL verification, we look at the whole SIF. So we're looking at the sensors, any interface devices such as interposing relays, barriers, etc., the logic solver, and any interfaces between the logic solver and the final element. All of that needs to be considered. And we work out usually the individual probabilities of failures on demand and then add them up to get an overall figure. But let's say here we have very low probability of failure on demand at the start. And over time, of course, what happens is that the probability of failure on demand will increase until we get to the point where we do a proof test. So if the demand occurs here at this point in time, the probability of failure on demand is pretty low. However, if it causes, or we get a demand here and that we have a failure, this would be a very high probability of failure on demand. So between these two, what value of PFD do we use? And here again, oops, what we say is failures are normally independent of demands by virtue of the fact that when we look at an independent protection layer, the justification for saying it's an independent protection layer is it's independent, meaning that if it fails, it cannot cause or cannot propagate a failure to another independent layer, and that fails too. So the two can't fail together, they have to be independent. So that's why we say if the events that cause a demand are independent from the equipment failures, then we can, coming back to our constant failure rate during useful life, we can take an average value. So therefore, if we look at how do we calculate, and this takes you back to your calculus, the area under the curve has to be calculated using an integral function. And this is the premise of Simpson's rule. So therefore, if we're looking at calculating a PF average, we need to look at the area under the curve. We need to integrate between 0 and t in our example. So the formula would come out to be the PF average is 1 over t integral of the probability of failure for time with respect to time, assuming constant failure rate again during useful life, this flat part of the curve. Then if that's the case, we can say that our PFD average now is approximately lambda d, because it's a failure on demand, so it's a dangerous failure, times our test interval divided by 2. So this is what we call the simplified equation. It's an approximate equation, but it's for low values of lambda, that's true. And the reason we can say this here is because of this constant failure rate over the useful life. Now if we look at this a little more closely, when we talk about probability of failure, we know that probability of failure doesn't have any units, but it does use a time period. And failure rate is different from that, but because failure rate is given in units of failures per time, so this is where we come into our fits. And we always use a failure per hour for our analysis. This is the smallest unit of time which is relevant. So even though probability of failure doesn't have units, it has to be done for a given time period. And of course, failure rates are the numbers of failures in a given time, and usually per hour. So we use this per hour. So for again, looking at the example, if the failure rate is 5 times 10 to the minus 8 failures per hour, or in other words, 50 fits, The probability of failure for a time interval of 1 hour, therefore, would be using our formula PFH equals 1 minus e to the minus lambda t, and that would give us our 5 times 10 to the minus 8, or 50 fits for a 1 hour interval. So again, we can, during our useful life, coming back to the useful life again, we can calculate a longer time interval using our rules of probability combination. And this is where we can use our complement rule, where basically the probability of success would equal 1 minus the probability of failure, and likewise the probability of failure would equal 1 minus the probability of success. So here, if we use that substitution, so we would say the probability of failure for 24 hours, it would be 1 minus, and here now we're saying 1 minus the probability of failure per hour, which would be success. And what this does, it simplifies the maths for us. So if we were using 5 times 10 to the minus 8 for a 24-hour period, we'd end up with 1.199 10 to the minus 6. And over a year, that would be 4.38 times 10 to the minus 4. So you can see it's a linear, doing this, we'd end up with a linear function. So if we come back to the terms reliability and unreliability, in reliability engineering, we use this one's complement, as I just said. The probability of success or reliability would be 1 minus the probability of failure, and vice versa. So in this case, if we said failure for the time period was equal 1 minus e to the minus lambda t, then of course substituting using our complement rule, we would say that the reliability would be e to the minus lambda t. Here again, constant failure rate. We could then use our exponential functions to calculate our metrics. And here again, this goes back into a lot of the calculus, but we're basically dealing with the area under the curve, and so we have to calculate that particular range. Also, here again, from math, we can approximate by a series of other functions when it comes to looking at this. E to the x is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. Now, if you can't remember what factorial is, 2 factorial is 1 times 2, 3 factorial is 1 times 2 times 3, 4 factorial is 1 times 2 times 3 times 4, etc. So you get the idea. So of course, if x is small, and generally when we're saying x in this case is going to be our failure rate times our time, and would tend to be small, then we can approximate that e to the x would be 1 plus x, because these terms would become much, much smaller and less significant. So it's a useful approximation. And then if we substitute for minus lambda t, then e to the minus lambda t would be approximately 1 minus lambda t. So we can say then that if we substitute there in this equation for e to the minus lambda t, you can see that we would be left with our unreliability function is approximately lambda t. And so for our probability of failure, that would be lambda t. And hopefully that's fairly straightforward and easy to see. But again, these are all predicated on this constant failure rate during useful life. So if we plot our approximation against our exponential equation, you can see that if we have probability of failure less than 0.1, then these two are relatively the same. So we won't have a significant error when our probability of failure is less than 0.1. And generally, when we're looking at failure rates, constant failure rate during useful life, these tend to be very small numbers. And so this can hold true. So here again, our variable t represents our time interval of operation. And of course, the longer the time interval, the higher the chance of failure. So this is what we would call our mission time. And here again, mission time shouldn't be confused with useful life, because mission time would be the time that the end user defines for the safety instrumented system. So sometimes end users will look at mission time and say, well, we have these final elements, and these final elements have to be refurbished or replaced every 10 years. And since these final elements are the biggest or the most difficult things to replace and refurbish, we might set our useful life, or rather our mission time, at 10 years. However, other equipment, some of the sensors, for example, may have a useful life of 5 years. So if we have a mission time of 10 years and the sensors have a useful life of 5 years, then we need to replace them every 5 years. So this is the difference. The mission time is chosen based upon end user practices. And usually when I teach the class, I ask them, you know, what sort of mission time do you use? And some will say, well, we tend to use 15 years, even though we know the valves have to be changed every 10 years, but 15 years is when we would probably do a full system upgrade. Or others will say 10 years. I've had some say 7 years. It just depends upon the mechanical integrity programs and what their policy is. But mission time is different from useful life. So again, if we give an example here, so we have a plant has operated for 5 years continuously. The process unit has to last for 50 years before complete replacement. Some of you may question that, but this is just an example. So at the end of each year, each 5-year period, the unit's shut down and overhauled. So of course, devices performing the safety function have been given the following useful life, which is again identified in the safety manual. So the pressure transmitter is 50 years, the actuator's 10, solenoids 5, gas detector 2. So here again, we have to overhaul or replace these devices before the end of their useful life. So what mission time do we use? 5 years might be a good choice, but gas detectors have to be replaced while the process is online. And therefore then we've got to consider bypassing and how we would design bypassing into the system of those devices. Or we would have to think about possibly having a redundant architecture to enable us to do that. The solenoid valves themselves will be replaced every shutdown, and again based upon economics. And the actuators are likely to be overhauled every 2 shutdowns. The pressure transmitters, in this case, would be replaced at least every 10 shutdowns. So it's important to consider this, and as I've said, most of the time end users will define what their mission time is. But it needs to be considered bearing in mind what the useful life is. And like I said, most of the time end users would tend to focus on final elements because they are the key things, the most expensive things usually to have to overhaul and replace. But it's really preference. When we talk about PFD average, you have to think about the notion of incomplete testing. And here again, what we look at, if we take our simplified formula of our PFD average, now we have to add into what we can call an effectiveness for the coverage of the proof testing. So this can be between 0 to 100%. And it's the effectiveness of finding dangerous faults. Hence, we're looking at our dangerous faults, our lambda D. But because there's no such thing as a 100% perfect proof test, you need to consider how much you can achieve. And what you'll find is that, in general, logic solvers can achieve very high levels of coverage, 98%, and certain smart transmitters can too. Problem always comes with the final element. Because of the nature of the beast, you're not going to be able to design a proof test to get that higher coverage on a final element. You might get 60–65% if you're lucky. So that means that every time we do a proof test, we're not getting all the way back to zero. So clearly what happens over time is every time we do a proof test, this line moves up. So our PF average or PFD average is going to continue to get worse. And at some point, you're going to cross the threshold between the current SIL level you're in to a lower SIL level. And this is important because here again, if we're following a run to fail policy, then what happens is, of course, the PFD average, once you get outside of the useful life, you're no longer in that constant failure rate section of the bathtub. So the concept of a PFD average goes out the window because you can't rely on the failure rate. It's unpredictable. It's not constant. So your PFD average disappears, and effectively you're going to end up with no SIL at all. So that's why you should not be running to fail. You need to look at this useful life and understand it. And one question I had was that, yes, you have to consider the logic solver in the mission time too. It's the whole device. It's a whole SIF rather. So you have to look at the sensors and everything. But typically, like I said, most of the time, the focus will be on the final elements. So you can see that even with keeping it in the useful life, we would still need to do our proof testing to maintain it. And obviously the higher the coverage, the better. But if we run outside of our useful life, we've lost any reliability that we thought we had. And that's why running to fail is not something that you should be doing. Okay, so just to summarize, the probabilistic analysis that's done when we do a PFD average calculation or even a PFH is based on the fact that we're using that constant failure rate during the flat portion of the bathtub curve. That's the useful life portion. And that, as I've said, is because we take the average over that useful life. It's a slightly more pessimistic approach, but it gives us pretty good results. And when we do PFD calculations, we're looking at, for low demand, the PFD average for the reasons we've stated. Again, constant failure rate, we need to know where's a good point to take, and we use the average value to take as our probability of failure on demand. The problem with run to fail is it ignores this useful life, and then it extends into the wear out portion of the bathtub where it's no longer constant and it's unpredictable. So we can't use that concept. Our MTTF becomes invalid and our PFD average becomes invalid. So we have no longer good reliability. This means then, of course, that the SIF integrity is going to be compromised during the wear out. So you will not be able to say you still have a SIL2, for example. This is something that people don't understand. And I've said when I usually teach the class, I ask the class, anybody here have a run to fail policy? And sometimes I get people saying, yes, we have that. So the culture really is important to understand because, yes, replacing equipment is not easy or cheap. But again, if you choose your equipment carefully, you'll have good numbers, good reliability, and you need to include that as part of your mechanical integrity. Proof testing, of course, is another thing that helps us maintain the SIF's integrity during the useful life and eventually over the mission time of the safety instrumented system. But here again, proof testing just gives you that opportunity to try and find potentially dangerous faults that your automatic diagnostics cannot find. So that's something that needs to be considered. and therefore the mechanical integrity programs should account for this useful life and should have a parts replacement program or a refurbishment program. And as I've said, this is normally down to the end user practices and policies. So here again, you may say that, okay, every 5 years we have a full plant shutdown and we'll do a full refurbishment of our final elements. That's fine, but you've still got to think about the logic solver and the other parts of the SIF. When do they need to be replaced? And so this is something that is very important. It should be in the SRS, but that information should come from the safety manual. So it's very important that you have the safety manual and that you understand what that useful life is for that piece of equipment. Because like I said, IEC 61511 uses this probabilistic analysis to figure out what the potential SIL is for the SIF. And then, because it's a performance-based standard, it expects you to periodically be measuring the performance of your system. And that would be looking at what sort of events have we had near misses, have we had failures? Are we running our proof testing correctly? Do we implement our mechanical integrity correctly? Are we replacing equipment at the end of useful life consistently? Because all of these things would fall into your leading and lagging indicators. And of course, your leading indicators are indicators that you can use to predict whether you're likely to have an incident or not. For example, if you're running to fail, if you're not running your proof testing correctly, then you're more likely to have an incident or a problem because of failure on demand. So these things are important, and that's the reason why you should not have a run to fail policy, because once you do that, once you get outside of the useful life, now you are no longer in that constant failure rate region, and therefore your PFD average and your SIL calculations are really null and void. Okay, so that is the end of it. Anybody have any questions? I've seen a couple. Let me ask this. Any of you want to privately let me know whether you have a run to fail policy or not at the moment? Yeah, I don't see anybody coming forward. It's either it's good because you don't. I see them now. Okay. So, well, that's good. Somebody says they're in the process of changing. I'm glad to hear that. There's another one. My question may have come to. Okay, so I might have another question later on. Yeah, see, a lot of people get confused between this useful life and mission time. And they often say to me, what's the best mission time to use? And as I've said, it really comes down to the type of process, the plant itself, and your mechanical integrity program, because here again, normally valves, depending on what they are, you need to consider when they have to be refurbished or replaced. And again, if it's, for example, an ammonia plant or a plant where it's severe service, if the valves are not chosen carefully enough, then you could end up having a lot of reliability problems. In fact, there's one client that we're helping at the moment, and they're in that very same situation, that they have a very corrosive application, and unfortunately the engineering company that chose the valves didn't consider this, and they've had a lot of premature failures as a result. But in general, if you do it right, then you can balance it. And the whole point of the safety life cycle is to balance this, being able to provide the right level of protection in an economic and cost-effective manner. So here again, run to fail is not a way to do it. There's a comment I've got. One of the difficulties is persuading maintenance people to replace seemingly serviceable equipment. Explaining all this useful life stuff to workshop people isn't easy. I fully agree with you, but this does come down to culture. Here again, culture has to come from the top. If they don't have the right safety culture, then it's going to be very difficult, because you'll be pushing on a rope, because you'll be fighting this, well, it ain't broke, why do we need to fix it type attitude, or we've never had a problem with this equipment before, why should I change it? Come across it all the time. But if you are an OSHA PSM site, if you using 61511 as your basically your RAGA recognized and generally good engineering practice, then this is very, very important to do. Also, if you're OSHA PSM, you have to have a mechanical integrity program which covers this. What else do I have here? Can I be allowed to ask a different question on functional safety? Yes, you can contact me directly. The email address is there. Also wondering how we can work out the percent coverage of the proof test on a final element. Well, again, if you're using certified equipment from a reputable agency, the equipment manufacturer has to provide you with a safety manual, and typically in the safety manual they will have a recommended proof test to achieve a certain coverage factor. The other thing is Excellencia can determine the proof test coverage just by looking at the type of equipment that's selected during the design, because Excellencia allows you to design your SIFs, and you can select from the SERH manufacturer's equipment, and typically if it's a preferred manufacturer, we would have some of their equipment. If not, there's generics that you can use, but Excellencia looks at the equipment and figures out a percentage proof test coverage that you can achieve. Excellencia also is sophisticated enough to be able to handle severe service and tight shutoff requirements. So the Markov model is modified according to whether you select severe service, and severe service can be corrosion, it can be contaminants, etc. As long as the device that you've chosen is able to handle severe service. Because if you select severe service but the device can't handle it, Excellencia will tell you that you need to choose a different device. And again, yes, at the end of the bathtub or near the bathtub curve, the coverage can be quite a lot higher. Well, again, like I said, because if you're using Excellencia, it's very easy to do, because Excellencia does it for you based upon all the parameters for that particular device. The constant failure rate during useful life is what the safety manual will talk about. They'll say if you do this, you can achieve this coverage. I think it's safe to assume that once you get outside of useful life, you really should consider your PFD as one, because you cannot guarantee that it will be able to service a demand. Any other questions? Okay, that's it's indeed difficult to pass this information on to maintenance or management, which is why, okay. Yes, I understand. It is very difficult. But knowing this and understanding this and showing that if they're committed to following 1511, then clearly everything is predicated on this constant failure rate during useful life. So that's the bottom line. If they don't follow useful life, you cannot rely on your SIF. It's as simple as that. So hopefully you'll have luck with trying to convince maintenance that this is what needs to be done. But really and truthfully, the question comes down to, are we committed to functional safety or not? Because you've only got to look at what happened with Buncefield, what happened with Texas City, what happened with Macondo. These were all preventable. The problem was the equipment, the maintenance, etc. wasn't done correctly because the culture wasn't there, the commitment wasn't there, everything was bottom line focused. And I always come back to dear old Trevor Kletz's statement. And he used to say, if you think safety is expensive, try an accident. Is there any study done to link economics with useful life justification? You can always look at doing life cycle cost analysis. And again, if you want, Excellencia does that for you. It's with anything. Yes, you can try and run to fail, but I'm saying to you now that if you run to fail and you have an incident and OSHA comes in and finds out that you have not followed RAGAGAP and best practice, then you're in for a very uncomfortable ride. I had 2 students on one of my classes, and when I asked them if they were OSHA PSM, and they said yes, and they told me that the reason they were in the class was because they had, for years, never had any problems. And the trouble is, of course, OSHA doesn't have enough people to be able to go in and audit every single site. So it's done on an exception basis. And these guys said, yep, we had an incident and we can't get OSHA off our backs. We've got fines, we've got this, we've got that. And of course, part of that is competency. So you can, there's no study done as such, but you can do it yourself. The point being is, how much will an accident cost you? And I can tell you that Macondo right now is nearer 60 billion. That's what it's going to cost BP. 60 billion. And Buncefield cost 1.6 billion. And Buncefield was back in 2005. So if you ever have an incident where somebody's killed or injured or there's an environmental release, the EPA will be all over you. The fines can be significant. Chevron had 2 fires within the space of 2 weeks at this one plant. They got fined 500 million because it was in California. How much would it have cost them to have avoided that? So anyway, if there are no more questions, I will thank you for your time, and please, if you think of anything else, you can see my email address below. Feel free to drop me a line. I'll be happy to answer any questions you have, and I thank you for your time. I will be doing, there's a couple more coming up that I'll be doing. One will be on leading and lagging indicators and why those are important to use. I've written a blog on that. If you're interested, you'll see the blog. So that's another webinar that's coming up. And then I will be doing one on why it's important to do functional safety audits. So thank you, everyone. I wish you a good rest of your day, wherever you are, and look forward to you attending another webinar soon.